Hello everyone. This is the sixth tutorial for ENGG 2430A, Probability and Statistics for Engineers. Today, we will mainly talk about cumulative distribution function, probability density function, and weak law of large numbers. So now, let's begin with cumulative distribution function. We have already learned that for a discrete random variable, we always use probability mass function to describe the distribution of the random variable. The probability mass function measures the probability of all possible values. And that always works well because the discrete alphabet is countable. But when it comes to the continuous case, probability mass function cannot show the distribution of the continuous random variable because the probability at any point is equal to 0. So we then choose the cumulative distribution function, which is abbreviated as CDF, to describe the distribution of the continuous random variable. The CDF characterizes the probability that x is less than or equal to a given value. But sometimes we want to see the probability that x lies close to a given number. Then we need probability density function, which is abbreviated as PDF. A continuous random variable has a probability density function fx if fx is non-negative for all possible x, and the probability that the random variable x lies between a and b equals to the integral of fx from a to b. If we make the length of the integral interval to be the infinite small one, x to x plus dx, we can think of fx dx as the probability that x falls within the interval. This gives an intuitive interpretation of PDF, and that's why we use the word density. Both CDF and PDF are very important concepts, and they can be derived from each other. Firstly, we can see that the CDF describes the probability that x lies between minus infinity and small x, which by definition of PDF equals to the integral of the PDF fx over the interval that x lies in. Then the PDF equals to the derivative of the CDF with respect to x. The PDF and CDF cannot only describe the distributions directly, but also play other important roles. We now introduce how to calculate the expectations of continuous random variables through PDF. The simplest example is the calculation of the mean. If we divide the real numbers into length delta intervals, when delta is infinitely small, the probability that x lies within one length delta interval is approximately fn delta times delta. Then we multiply x equals n delta with the probability and sum all them up. We will get the mean of the random variable. This summation is then, by definition, equals to the integral of x fx over the whole interval. Similarly, variance of a random variable can be obtained by taking the integral of x minus mu squared times fx over the whole interval. Repeat this similar procedure, we can get the expectation of a general function of a random variable. Expectation of gx equals to the integral of gx times the PDF fx of the whole interval. This is a very useful result. We will use it repeatedly in our study. And there will be an example about this in our later discussion. We have just introduced the CDF and PDF for one continuous random variable. Recall that for multiple discrete random variables, we have a joint PMF, which describes the joint distribution of multiple discrete random variables. For multiple continuous random variables, we also have corresponding joint CDF and joint PDF. Similar as the univariate case, the joint CDF for two continuous random variables is defined as the probability that each variable is less than or equal to some value respectively. And the joint PDF is similarly the partial derivative of the CDF with respect to each variable. We can also use joint PDF to calculate the expectation of multiple random variables, and all about this is the same as the univariate case. We will see an example later. Then if we want to see the distribution of some one variable, we are referred to the marginal PDF, which is obtained by taking integral of the joint PDF with respect to all the other variables over the corresponding whole interval. Okay, after all the boring concepts, let's come to an example where we will study the distribution of some function of a random variable. Suppose we have a random variable uniformly distributed over 0, 1. Then the random variable is squared due to some reason. Now we want to know the CDF and the PDF of the squared variable y. To solve this problem, we denote x as the uniform random variable. Then y equals x squared, and it appears that y also lies between 0 and 1. The CDF of y, by definition, is the probability that y is less than or equal to small y. Since y equals x squared, the CDF then equals to the probability that x squared is less than or equal to small y. Since all we are concerning about lie between 0 and 1, the function y equals x squared has an inverse function x equals square root y. Then the CDF becomes the probability that x is less than or equal to square root y, which is by definition the CDF of x at square root r. Since x is uniformly distributed, we can then easily obtain the CDF of y, and is shown as the blue curve. At last, the PDF is just to take the derivative of the CDF, which results in the red curve. The basic method to deal with the transformations of random variables has already been illustrated here. We will have a practice in our later discussion. Now let's come to the last topic today, the weak law of large numbers. In the previous lectures, we know that in real life, we often need sampling to estimate the population. Then, how can the samples reflect the population? The weak law of large numbers will tell us how the samples reflect the population mean. Suppose we have a sequence of IID samples x1 up to xn with finite mean mu. Then the probability that the sample average is somehow away from the population approaches zero as n goes infinity. Intuitively, that is, when sample size is very large, the sample average will approach the statistic mean. Or we say the sample average converges to the mean in probability. Next, we provide a proof for the weak law of large numbers using Chebyshev inequality. Suppose the finite variance of the IID random variables is sigma squared. Then we can get the variance of the sample average due to the mutual independence of the random variables and some knowledge in the last several lectures. The mean of the sample average equals to the expected value, which is much more easier to obtain. Then all remains is to use Chebyshev's inequality on the sample mean, which yields the probability that the sample average lies epsilon away from the expected value is less than or equal to sigma squared over n epsilon squared. And this probability approaches zero as n goes infinity. We now finish the proof. At last, we give an example of the application of weak law of large numbers. During a Bernoulli experiment, event A occurs with probability p. We now consider n independent repetitions and denote xi as the ith Bernoulli random variable. That is, xi equals to 1 if A occurs during the ith experiment, and equals to 0 if A does not occur. We then get the Bernoulli distribution of xi and the expected value. Then the empirical frequency Fn equals to the average of x1 up to xn. By the weak law of large numbers, we have Fn approaches p as n goes infinity. This indicates that when n is very large, the empirical frequency Fn of A is very likely to be close to p, the probability of A. Okay, this is the end of the tutorial. Thank you.